Hey guys, I want to ask you something that I think most people never really consider. Right now, as you're sitting or lying there, you're inside a galaxy, not looking at one from far away, but actually inside one, surrounded by hundreds of billions of stars, most of which you'll never see because dust blocks your view, spinning around a supermassive black hole at over 800,000 kilometers per hour. When you look at that faint band of light stretching across a dark sky, you're seeing your own galaxy from the inside. Have you ever stopped and tried to imagine what that actually means? Like, really tried to picture where you are in all of this? Let me know in the comments. I'm curious if people think about their galactic address. Tonight, we're taking a tour of our home galaxy, the Milky Way. We'll explore its structure, from the dense core at its center to the sparse halo surrounding it all. From the spiral arms, where new stars form, to the quiet regions between them. We'll trace our sun's location and motion, examine what lies at the galactic center, and understand how astronomers piece together the shape of something we can only observe from within. This is a calm journey through the architecture of our cosmic neighborhood. The galaxy that contains everything humans have ever known. The vast collection of stars and gas and dust that we call home. Let's begin with what we can observe from Earth on a clear night, far from city lights. A faint luminous band stretches across the sky. Ancient observers from different cultures gave this band various names. The ancient Greeks called it Galaxius Kyklos, meaning Milky Circle. The Romans called it Via Lactea, the Milky Way. These names described its appearance. A dim, glowing path resembling spilled milk across the darkness. For thousands of years, people wondered what this band represented. Some cultures saw it as a river, others as a path taken by souls. It wasn't until Galileo turned his telescope toward this band in 1610 that humanity began understanding its true nature. Through his simple telescope, Galileo observed that the Milky Way wasn't a continuous glow, but consisted of countless individual stars packed so densely that they blended together when viewed with the naked eye. This discovery revealed that the band represented not a substance, but a vast collection of distant stars. But what arrangement of stars would create this band stretching across the sky? Why would stars concentrate in this particular pattern? The answer, though it seems obvious now, took centuries to fully establish. We're inside a flattened disk of stars, and when we look along the plane of this disk, we see many stars in a concentrated band. When we look perpendicular to the plane, above or below the disk, we see far fewer stars. Imagine standing inside a forest. Look horizontally through the trees, and you see trunks extending in every direction, creating a dense view. Look straight up, and you see mostly empty sky with occasional branches. The Milky Way's appearance follows this same principle. We're embedded within a disk of stars, looking through it. Understanding our position within this disk required careful observation and measurement. In the early 20th century, astronomer Harlow Shapley studied globular clusters, dense spherical collections of stars that orbit the galaxy. He noticed that these clusters appeared concentrated in one particular direction, toward the constellation Sagittarius. Shapley realized that globular clusters must orbit the galaxy's center, and their concentration in one direction meant that center lay in that direction. By measuring distances to these clusters, he estimated how far we lie from the galactic center, though his initial estimates proved too large. Later refined measurements revealed our distance to be approximately 26,000 light-years from the center. This places us neither at the edge nor at the center, but roughly halfway out in the galactic disk. If the Milky Way were a city, we'd be living in the suburbs. Not downtown, but not in the countryside either. The Milky Way is classified as a barred spiral galaxy. meaning it possesses both spiral arms and a central bar-shaped structure. Understanding this structure proved challenging because we observe from within the galaxy, with our view obscured by dust that blocks visible light. Radio observations proved crucial to mapping galactic structure. Neutral hydrogen, the most abundant element in the galaxy, emits radio waves at a specific wavelength of 21 centimeters. These radio waves penetrate dust easily, allowing astronomers to detect hydrogen throughout the galaxy. By measuring the Doppler shift of these hydrogen emissions, astronomers determined velocities of gas clouds at different locations. Objects moving toward us show wavelengths shifted shorter, while objects moving away show wavelengths shifted longer. Combined with models of galactic rotation, these velocity measurements reveal distances, allowing construction of maps showing where hydrogen concentrates. These maps revealed spiral structure. The Milky Way contains several major spiral arms, regions of enhanced density where stars form actively. The exact number of arms remains somewhat uncertain, with different observations suggesting either 2 major arms or 4 arms of varying prominence. The Sun resides in the Orion Arm, also called the Orion Spur, a minor arm or spur located between 2 larger arms called the Sagittarius Arm and the Perseus Arm. Our location in this relatively quiet region, away from the dense star-forming regions of major arms, may have allowed our solar system to evolve undisturbed for the billions of years necessary for complex life to develop on Earth. The galactic disk, where we reside, stretches approximately 100,000 light-years in diameter. This disk rotates, but not like a solid body. Instead, stars at different distances from the center orbit at different rates, though with velocities that remain roughly constant rather than decreasing with distance as planetary orbital velocities do. This rotation creates the spiral arms. Spiral arms represent not fixed collections of stars but density waves, regions where stars and gas temporarily concentrate as they orbit. Think of traffic on a highway. Cars move through a traffic jam, entering from behind, slowing briefly, then accelerating past. The jam persists even though different cars occupy it at different times. Similarly, stars move through spiral arms, which persist as features even though their stellar population constantly changes. The enhanced density in spiral arms compresses gas clouds, triggering star formation. This explains why spiral arms appear bright and blue. They contain many young, hot, massive stars that shine brilliantly but expire quickly. The regions between arms contain older, longer-lived stars that emit less light, making interarm regions appear dimmer. Our Sun, a middle-aged star approximately 4.6 billion years old, formed from a gas cloud somewhere in the galactic disk. Since formation, it has completed roughly 20 orbits around the galactic center, with each orbit taking approximately 230 million years. The last time our solar system occupied its current position relative to the galaxy, dinosaurs were first appearing on Earth. Mammals had not yet evolved. The disk itself contains structure beyond the spiral arms. It divides into a thin disk and a thick disk. The thin disk, perhaps 1,000 light-years thick, contains most of the gas, dust, and young stars. The thick disk, several thousand light-years thick, consists of older stars with less organized motion. Stars in the thin disk move in nearly circular orbits close to the galactic plane. Stars in the thick disk follow more elliptical orbits inclined at various angles to the plane. This difference reflects formation history, with the thick disk representing older stellar populations formed when the galaxy was younger and less organized. At the center of the disk, obscured by dust clouds that block visible light, lies the central bulge, a roughly spherical concentration of stars about 10,000 light-years in diameter. This bulge contains primarily old stars. formed early in galactic history, moving on complex orbits in 3 dimensions, rather than the orderly circular paths characteristic of disk stars. Infrared observations, which penetrate dust more effectively than visible light, reveal the bulge's structure. It appears somewhat elongated, forming a bar extending perpendicular to the spiral arms. This bar, approximately 27,000 light-years long, rotates more slowly than the disk, completing a rotation roughly every 180 million years. The bar influences galactic structure. Gas moving in the disk encounters the bar's gravitational field, which can funnel gas toward the center or launch it into spiral arms. The bar's gravitational effects shape orbital patterns throughout the inner galaxy, affecting where star formation occurs and how gas distributes itself. At the very center of the galaxy, within the dense core of the bulge, lies something remarkable. Observations of stellar motions near the galactic center reveal stars orbiting an invisible massive object at tremendous speeds. Some stars complete orbits in only 16 years, reaching velocities exceeding 5,000 kilometers per second. Only one explanation fits these observations. A supermassive black hole resides at the galactic center. This object, called Sagittarius, a star, contains approximately 4 million times the Sun's mass compressed into a region smaller than Mercury's orbit around the Sun. The black hole itself emits no light, but matter falling toward it releases enormous energy before crossing the event horizon. Observations at radio, infrared, and X-ray wavelengths reveal this activity. Occasionally, when a gas cloud or star passes too close, material gets captured and heated to millions of degrees, producing bright flares detectable across the electromagnetic spectrum. Most of the time, however, Sagittarius, a star, remains relatively quiet. The supermassive black hole at our galactic center accretes material slowly compared to active galactic nuclei in other galaxies, making the Milky Way's center far less luminous than it could be. Supermassive black holes appear to reside at the centers of most large galaxies. Their masses correlate with properties of their host galaxies, suggesting black holes and galaxies co-evolve, influencing each other's growth through feedback processes. Understanding exactly how this relationship develops remains an active area of research. Beyond the disk and bulge, surrounding the entire galaxy, extends the galactic halo. This roughly spherical region, stretching perhaps 300,000 light-years from the galactic center, contains a sparse population of old stars and globular clusters. Globular clusters, dense spherical collections containing hundreds of thousands to millions of stars, orbit throughout the halo on elongated paths that carry them far above and below the galactic disk. These clusters contain some of the oldest stars known, with ages exceeding 12 billion years, nearly as old as the universe itself. The stars in globular clusters formed from gas with very low heavy element content, indicating they formed before many stellar generations had enriched the interstellar medium with fusion products. Their composition provides clues about conditions in the early universe, when galaxies first assembled. Individual halo stars, scattered between the globular clusters, show similarly low heavy element abundances and old ages. Many follow highly elliptical orbits inclined at steep angles to the galactic plane, some even orbiting retrograde, opposite to the disk's rotation direction. These unusual orbits suggest many halo stars didn't form within the Milky Way originally. Instead, they likely belong to smaller galaxies that merged with the Milky Way billions of years ago. When galaxies merge, their stellar populations mix, with stars from the smaller galaxy often ending up in the larger galaxy's halo on disturbed orbits. Evidence for such mergers appears in stellar streams, elongated concentrations of stars with common motion stretching across the sky. These streams represent the tidally disrupted remnants of smaller galaxies, or globular clusters, torn apart by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy, currently merging with the Milky Way, has created multiple streams of stars and globular clusters wrapped around our galaxy. The halo contains another mysterious component, dark matter. This invisible substance, interacting primarily through gravity, comprises roughly 90% of the Milky Way's total mass. We detect its presence through its gravitational effects on visible matter, but its fundamental nature remains unknown. Measurements of stellar velocities in the outer galaxy reveal that stars orbit faster than visible matter alone could explain. The gravity from visible stars and gas proves insufficient to keep these fast-moving stars bound to the galaxy. Dark matter, distributed throughout a massive halo extending beyond the visible galaxy, provides the additional gravity necessary to explain observed motions. The Milky Way's dark matter halo likely extends several 100,000 light-years from the galactic center, far beyond where visible stars concentrate. This halo's total mass probably exceeds 1 trillion solar masses, dwarfing the few hundred billion solar masses contained in visible stars and gas. Understanding dark matter's distribution helps explain galactic dynamics, but the particle nature of dark matter remains one of physics' great unsolved problems. Experiments search for dark matter particles through direct detection or by looking for signals from dark matter annihilation or decay. So far, none have definitively identified dark matter, leaving its identity mysterious. The Milky Way doesn't exist in isolation. It belongs to the local group, a small cluster of galaxies bound together by mutual gravity. The local group contains approximately 80 known galaxies spread across a region roughly 10 million light-years in diameter. The largest member, the Andromeda galaxy, lies approximately 2.5 million light-years away. Andromeda, also a barred, spiral galaxy, appears slightly larger than the Milky Way, containing perhaps 1 trillion stars compared to our few hundred billion. Andromeda and the Milky Way, the two dominant galaxies in the local group, are approaching each other at roughly 120 kilometers per second. In approximately 4 billion years, the two galaxies will begin their first close passage, gravitationally disrupting each other's structures. Over the following several billion years, repeated passages will gradually merge the two galaxies into a single larger galaxy, probably an elliptical galaxy rather than a spiral. This merger will transform both galaxies' structures, but individual stars will rarely collide due to the vast distances between them. The Milky Way also hosts numerous smaller satellite galaxies, dwarf galaxies gravitationally bound to us and orbiting through our halo. The most prominent, the large and small Magellanic Clouds, appear as fuzzy patches in the southern hemisphere sky, visible to the naked eye from dark locations. These irregular dwarf galaxies, containing billions rather than hundreds of billions of stars, orbit the Milky Way while continuing to form new stars from their gas reservoirs. Gravitational interactions with our galaxy gradually strip gas and stars from these satellites, contributing to the Milky Way's ongoing growth. Dozens of even smaller dwarf galaxies orbit throughout the local group, many discovered only recently through careful sky surveys. These ultra-faint dwarfs, containing only thousands to millions of stars, represent the least luminous galaxies known. Detecting them requires sophisticated image processing to identify their faint stellar populations against background contamination. The Milky Way's formation history involves both growth through mergers with smaller galaxies and gradual accretion of gas from the intergalactic medium. The oldest stars, found in the bulge and halo, formed over 12 billion years ago when the galaxy was just assembling from smaller fragments. The disk formed later as gas settled into a rotating plane and continued forming stars over billions of years. The thin disk, containing the youngest stars, represents the most recent phase of galactic evolution, ongoing star formation from gas concentrated in spiral arms. Chemical evolution accompanied structural evolution. The first stars formed from nearly pure hydrogen and helium, the only elements present in the early universe. As these stars lived and died, some exploding as supernovae, they enriched the interstellar medium with heavier elements created through fusion. Each successive generation of stars formed from progressively enriched material. By the time our Sun formed about 4.6 billion years ago, the interstellar medium contained roughly 2% heavy elements by mass, enough to form rocky planets like Earth. This ongoing enrichment continues today. Massive stars currently forming in spiral arms will live briefly, tens of millions of years, before exploding and scattering newly synthesized elements back into the interstellar medium. Future stellar generations will incorporate this material, gradually increasing the galaxy's heavy element content. Star formation rates have varied throughout galactic history. The Milky Way likely formed stars much more rapidly in its early history, when gas densities were higher and galaxy mergers provided additional fuel. Today, star formation proceeds more slowly, though it continues in molecular clouds throughout the disk. Observations of gas and dust reveal ongoing star formation. Giant molecular clouds, concentrations of cold gas spanning tens to hundreds of light years, serve as stellar nurseries. Within these clouds, dense regions collapse under their own gravity, fragmenting into multiple protostars that eventually ignite fusion and become stars. The Orion Nebula, located approximately 1,350 light-years away, represents the nearest major star-forming region. This glowing cloud, visible to the naked eye as a fuzzy patch in Orion's sword, contains hundreds of young stars less than 1 million years old, still surrounded by remnant material from their formation. Throughout the Milky Way, thousands of such regions actively form stars. Radio, infrared, and visible observations reveal these nurseries at various stages. From cold dark clouds just beginning to collapse to bright nebulae illuminated by newly formed massive stars, to dispersing clouds where stellar winds have blown away remaining gas. This cycle, gas collapsing to form stars that then disperse remaining gas through winds and supernovae, continually processes the interstellar medium, material cycles between stars and the space between them, with each cycle enriching the medium's chemical composition. The galaxy we observe today resulted from nearly 14 billion years of this evolution. Structure emerged as gas and dark matter collapsed under gravity. Stars formed, lived, and died, enriching subsequent generations. Smaller galaxies merged, contributing their stellar populations. Gas continued accreting from the intergalactic medium, sustaining ongoing star formation. Understanding this history requires combining observations of nearby stars and gas with studies of distant galaxies at various ages. We cannot watch the Milky Way evolve over billions of years, but we can observe many examples of galaxies at different evolutionary stages, reconstructing typical evolutionary paths. The Milky Way represents one particular outcome of galactic evolution, a large barred spiral galaxy currently forming stars at a moderate rate in a relatively quiet environment. Other galaxies evolved differently, affected by different initial conditions, merger, histories, and environments. Elliptical galaxies, for instance, show little ongoing star formation, their gas having been consumed or stripped away. Irregular galaxies often display active star formation in chaotic patterns, lacking the organized structure of spirals. Understanding this diversity, how different galaxies form and evolve along different paths, remains a major goal of contemporary astronomy. Our location within the Milky Way provides both advantages and challenges for studying it. We can observe nearby stars in exquisite detail, measuring their properties with precision impossible for stars in other galaxies. We can map local gas distributions, trace stellar motions, and resolve individual stellar populations. However, our interior position obscures the overall structure. Dust blocks visible light from the galactic center and from regions along the galactic plane. We cannot easily see the spiral arm's overall pattern or determine precisely how many major arms exist. Observers in another galaxy would see the Milky Way's structure more clearly than we can from within. Combining multiple observation methods helps overcome these limitations. Radio observations reveal neutral hydrogen distribution, tracing spiral structure. Infrared observations penetrate dust, revealing the bulge and center. Visible observations show nearby stars. Space-based observations avoid atmospheric interference. Together, these techniques create a comprehensive picture of galactic structure. Future observations will continue refining our understanding. The European Space Agency's Gaia mission, launched in 2013, is measuring precise positions and motions of over 1 billion stars. This unprecedented data set reveals stellar populations, traces orbital patterns, and maps three-dimensional galactic structure with remarkable detail. Gaia's measurements show that the Milky Way's disk isn't perfectly flat, but exhibits warping, bending away from the plane at large distances from the center. This warp likely results from gravitational interactions with satellite galaxies or from uneven dark matter distribution in the halo. The data also reveals that the galaxy experienced a significant merger event approximately 10 billion years ago, when a dwarf galaxy called Gaia Enceladus collided with the young Milky Way. Stars from this merger event, identified by their unusual orbital properties and chemical compositions, now populate the galactic halo, persistent evidence of ancient violence. Understanding the Milky Way helps contextualize our place within the cosmos. Every civilization that ever existed, every human who ever lived, every thought ever thought, occurred within this one galaxy. Our entire history, biological and cultural, unfolded in a tiny region of the galactic disk, on one planet, orbiting one ordinary star among hundreds of billions. Yet this galaxy itself represents only one among hundreds of billions of galaxies spread throughout the observable universe. The Milky Way, while enormous by human standards, occupies no special position cosmically. It's simply one large spiral galaxy among countless others, following the same physical laws, undergoing similar evolutionary processes. This perspective, understanding ourselves as inhabitants of one galaxy among many, developed only recently in human history. For most of our existence, humans didn't know galaxies existed. The Milky Way appeared simply as a luminous band, its nature mysterious. Only in the past century did we establish our cosmic address, recognizing ourselves as residents of the Milky Way, a barred spiral galaxy in the local group, part of the Virgo supercluster, itself a small part of the observable universe. The journey from ancient observers wondering about the Milky Band across the sky to modern astronomers mapping galactic structure in 3 dimensions represents remarkable progress in understanding our cosmic environment. Yet many questions remain. How exactly did the Milky Way form? What determines its structure? How will it evolve in the future? What is dark matter? Each answered question reveals new mysteries. Each observation refines understanding while exposing gaps in knowledge. This ongoing process, combining observation with theory, continues expanding our understanding of the galaxy we call home. As we conclude this tour of the Milky Way, we return to our starting point. Earth, one small planet in orbit around one ordinary star, located in a minor spiral arm approximately halfway from the galactic center to the edge. From this vantage point, embedded within the structure we study, we observe our home galaxy, mapping its shape, tracing stellar motions, and piecing together its history. The Milky Way surrounds us, though most of it remains invisible to our eyes, hidden by dust or simply too distant and dim to detect without instruments. Yet through careful observation across many wavelengths, through theoretical modeling of galactic dynamics, through studies of stellar populations and chemical compositions, we've mapped this vast structure, our cosmic home. We drift through this galaxy at hundreds of thousands of kilometers per hour, following the Sun on its orbit around the galactic center, part of the vast rotation that has continued for billions of years and will continue for billions more. The galaxy evolves slowly, imperceptibly on human timescales, its structure shaped by gravity, acting across immense distances over enormous stretches of time. Understanding this galaxy, this collection of hundreds of billions of stars bound together by gravity and organized into elegant spiral patterns, helps us understand our origins. The atoms in your body formed in stars, some in the early Milky Way, others in galaxies that merged with ours billions of years ago. You consist literally of processed galactic material, organized temporarily into patterns capable of contemplating the galaxy that gave rise to you. The Milky Way, this vast collection of stars and gas and dust and dark matter, represents more than just our physical location. It represents our larger context, the cosmic structure within which all human experience has occurred, the stage upon which life on Earth emerged and evolved. We are, in a very real sense, products of galactic evolution, made possible by billions of years of stellar birth and death within this galaxy. Tonight, if you have the opportunity, go outside and look at the sky. If you're fortunate enough to be far from city lights, you might see that faint band, the combined glow of countless distant stars, stretching across the darkness. You're seeing the Milky Way from within, observing your own galaxy, the structure that contains everything humans have ever known. And remember, as you look at that band, you're not just observing distant stars. You're seeing home, not just Earth, not just the solar system, but the entire galaxy, the vast cosmic structure we inhabit, the collection of hundreds of billions of stars that gave rise to our sun, our planet, and ultimately, ourselves. Good night.